Okay, everybody should have had a chance to join up here, so we're ready to start a session on IT project estimating. Okay, so what we're going to be covering here is a kind of a brief summary of a longer tutorial that I'll be teaching during the conference. So it's kind of an introduction to that class, if you will. But we're going to be covering some really good material. My background, I'm one of the few people out there really that specializes in software cost estimation, model development, and in IT model development. So there's not a lot of people that specialize in information technology estimating in general, but there's an even smaller number of people that specialize in developing the models themselves. So Capers-Jones, Barry Beam, and some others. As part of that and part of my ongoing work, I do a lot of articles, a lot of lecturing. I've written a lot of books, 27 books now, and also a lot of professional certifications, as you can see here. And one of the big areas is we want to improve accuracy. So when we're talking about accuracy, it's important to recognize that there's two different numbers that we're looking at. A lot of times when people talk about software cost estimation, they're thinking, what's my plus or minus range, or how good are the estimates relative to the actuals? And there's really two different numbers that we need to look at. The first is the mean error, and the mean error is defined as the average error across a statistically significant number of estimates. So if we're dealing with, for example, change requests on a very large project, it would mean that we would have a statistically significant number of change requests and then average the errors across that. Or perhaps we're talking about a portfolio of projects within an organization or within a division. So the mean error, we should be able to get it down to a very accurate number, because that mean error, some of the estimates will be too high, some will be too low, but they should balance out. And when I talk about a statistically significant sample of estimates, you can be sure that if you have 30 or more, that is statistically significant. I actually find that if we get to numbers around 15 or so, that normally that this will work out. So the mean, we want to have that be within plus or minus 10% normally. And for the more detailed estimates, once we understand the scope better, normally plus or minus 5%. The other number that we want to look at is for a given single point estimate. So for a given change request or for a given project, what's the standard deviation of that estimate? So how sure are we about that particular number? And there we're talking standard deviations. And for a high-level estimate, a standard deviation of 25% is reasonable. And for a scope level estimate, a standard deviation more in the 15% range is reasonable. It can be lower than that if you're doing repetitive type work. The second reason for formal estimation is to reduce the time spent estimating. The bottom-up estimation approach, or estimation by going around and gathering up estimates from individuals, is very labor-intensive. There's a large number of people that are involved in a project, large number of roles that are involved in a project, testers, project managers, developers, and so on. And for each of those roles, you need to have somebody that, number one, reads through all the different requirement specs that are out there and available, understands what the work needs to be done, so they need to gather and get an understanding of the project. They need to attend a lot of meetings typically. And so you have a lot of effort that's spent in order to get all the different pieces of the estimate, and then you have to compile that. Whereas if you have a formal estimation approach that's supported by some kind of modeling, you can have a much smaller number of people that need to read the requirement specs, that need to understand the requirements and be involved in that. And so it basically can result in a large savings in terms of time and money. And then you get some side benefits. You've got things like faster time to market. You've got things like better estimation processes that are more compliant with things like CMMI or SPICE or ISO. And you have the ability to do benchmarking, because as long as your estimation involves gathering up direct effort estimates from your testers and from your developers and so on, you really don't have anything to benchmark against, because you don't have a critical component of benchmarking, which is size. The only measure that you have of size is the estimated person hours of effort. So you don't have any other universal size measure such as function points or source lines of code or UML points or story points or something like that. So by doing formalized estimation, by definition we're going to have some kind of a size measure. If we do it right, that size measure will have some benchmarking ability. And then we can do things like comparison with peers. So how are we doing relative to other companies like ours? And we can do comparison over time. So for example, is our productivity getting better or worse over time? Is our quality getting better or worse over time? So what are some typical reasons to estimate? Well, in a government perspective, we're going to need to do budgeting. We're going to need to do feasibility study reports prior to it. So we can't just wait. We can't just say, well, we'll wait and let the vendor do the estimation and see what they come back with. We've got to do some budgeting. We've got to do feasibility studies. We also have to do independent government cost estimates if we're a government agency. So for example, we want to be able to validate that the vendor proposals are in a reasonable range. There's a lot of situations, especially on very large and very complicated projects, where despite our best efforts, we might only get one proposal back in. And in that situation, we want to be able to have a independent government cost estimate for reasonableness purposes. If there's a high-risk project, we want to make sure that we're not getting in over our head. If the project is coming in and it's got a budget of $50 million, and that's a large budget for our organization, we want to make sure that that doesn't turn into a $150 million project. We can also use these estimates to do alternative analysis. One nice thing about formal estimation is that it's relatively easy to get in there and make adjustments to the input parameters and then look at what the output results are. So it's relatively, doing the initial estimate is where the work is. And then it's relatively easy to do 3 or 4 different alternatives, compare those results, which then allows you to do things like make versus buy or other alternative analysis. And then finally, even if we're going out for bid and we're going to have the vendors come back in with the proposals to do the work, we still have to have some way to estimate the government component of the work. So the government still has responsibility for things like, well, doing the acquisition, first of all, obviously, but then ongoing responsibility for oversight, contract administration, approval of deliverables, review of deliverables, et cetera. And so we need to have some way to estimate that government component of the work. Now, the idea of estimation is very simple. The concept that we're going to try to follow is very simple, which is we want to follow the Steve Jobs principle, which is do a lot of work up front. Work very hard up front to make everything as simple as possible downstream on an ongoing basis. So the same concept applies to formalized estimation. We want to do a lot of work up front to understand and to standardize the processes and to set the parameters and to set the configuration and to review the historic data and so on so that we can do the calibration. So we do all of this work, and the end result is that the ongoing estimation process is very simple because we've done that work up front to identify elements that can be preset, and we can just use those preset variables then going forward. Now, when we're doing estimation, estimation itself follows a life cycle, very much like the software life cycle. So we've got, we're stepping across, we've got some kind of an engagement process, we're doing an assessment, we're doing a specification and planning process, the actual build process, and then test and validate and deliver. And so as we go across here, we find that there's going to be a series of estimates that are done. You normally don't do a single estimate because at the beginning you're going to need to do like a rough order of magnitude type estimate. As you move farther across, you're going to have additional detail, you're going to have better business requirements, so you want to do another estimate. Then as you go even farther, you're going to have more of a detailed design, you're going to have the best data possible prior to really getting into the bulk of the effort, and so you can do an additional effort. What we want to do is have a process that works at all these different levels without radically different changes to the way we do it. What we want to do is be dealing with perhaps slightly different input variables, but we want the process itself and the methodology itself to be as consistent as possible. Now, another thing that I like to point out to people is that estimation, the majority of your estimation models, your parametric estimation models and so on, are really all about coming up with an estimate of what we think the development effort is likely to take, a most likely number in terms of the development effort. And that tells you part of the story because, in fact, normally it's the bulk of the story, but it tells you part of the story. Because the other part of the story is that we have to deal with is risk. So if we look at the risk model or the risk life cycle, that involves identifying risks, then doing a qualitative analysis to kind of sort that list of risks, and then doing a quantitative analysis to actually quantify the likelihood and the costs of the various risks so that we can identify the risk exposure. And then based on that understanding of what are the major risks we're concerned about, what's our exposure based on that risks, now we want to reduce that exposure. And the way we reduce that exposure is number one, by doing risk response planning. So we're looking at mitigation type activities. A classic example that people give is buying insurance. But in the software world, there's a lot of other mitigation activities that we can do as well. I mean, we can hire consultants that are high-priced consultants that are available to us to do some expert guidance at some critical points in time. We can have some face-to-face interface control working meetings to help with some of those interfaces. There's just a lot of mitigation type work that we can do that's really designed to reduce risk. And so if we look at those mitigation type activities, many of those activities will have a cost associated with them, the cost of the insurance or the cost of the higher price consultant, etc. And so we need to budget for that. So we need to have those risk response funds available. We also need to have some contingency funds for dealing with the situations where risks do start to become a problem and where our response planning involves additional costs, and then we would need to have contingency funds that were available to support that. And then finally, we'd like to have a management set aside that's available for the things that we didn't anticipate, the risks that are coming in that were not something that we anticipated. So that management reserve would be valuable for us. Now, in terms of looking at estimation, there's and if you'll just give me a second here, I'm going to unplug this. There we go. All right, in terms of looking at estimation, when we're talking about estimating models, there's a lot of different models that are out there. I mean, you've got Kokomo 2, you've got the models that are built into SLIM, you've got the models that are built into Accelerplan that are built into these different products. And you've got a lot of different models even within that because you've got models for software development, you've got models for data conversion, you've got models for, there's just a lot of different models. But all of those models have some core concepts that are in place. So let's talk about that a little bit and make sure that we've got an understanding of some of these core estimation concepts. We always want to start with some kind of measure of size. Now, in bottom-up estimation, we're starting with a measure of activity. So we start with, if we're doing bottom-up estimation, we start with, well, what are the types of activities we have to do? We have to do project management, we have to do development, we have to do testing. And so we're going through and making a list of activities so that we can identify the roles, so that we can identify the role owners, so that we can get those role owners to tell us what their work component will be. But in a model-based approach to estimation, we don't start by looking at activities. Instead, we look at what's going to be delivered. So we're looking at what are the work components that at the end of the project are going to be left behind as the value added. What did the project create? And so I'm calling these high-level objects. So these are high-level representations of why we're doing this project, what business value are we providing as part of doing this work. So some examples of high-level objects would be pages on a website, reports, tables in a database, interfaces that are working, call tree options, and voice message recordings, deployed environments. So there's a lot of different, depending on the domain that we're trying to estimate, the high-level object list may vary, but there is this set of, this idea that why are we doing this? What are we delivering? Then as we move farther across, there's going to be some adjusting variables that are project-specific adjustments that are important in terms of estimating effort. These are going to be things like the experience of the team working with this set of tools and working with this application. Perhaps how well written this reusable application is. There may be things like, is this a classified project or not? There's just a lot of different variables that allow us to adjust things. For example, in IFPUG, we have the value adjustment factor, which allows you to adjust for this. In COCOMO 2, we have the COCOMO 2 environmental factors. And in a lot of models that are developed, pretty much all the models that are developed, there's going to be some kind of adjusting factors. So now we can take our standardized high-level object catalog for domain. We can apply the adjusting factors to adjust to this particular project. And then we need to do somehow to convert those high-level object-related outputs into effort. And we do that with productivity curves. And the reason they're a curve as opposed to a line is because for every domain, there's either going to be economies or diseconomies of scale. And so the difference between an economy of scale and a diseconomy of scale is simply the shape of the curve. And if there was something that for whatever reason was linear, well then it would just be a line instead of a curve. But basically we're going to have what's in effect a graph, and we're going to look up the adjusted high-level object value on that graph, and we're going to come up with a translation to person-hours of effort. So by doing this for a given project or for a given domain of a project, we can apply this method, and what we end up with is the total effort. And then with another curve lookup, we can end up with the total duration. So now we've got effort and duration. And when we talk about calibration, part of it is picking what are the right high-level object catalogs, what are the right adjusting variables, and so on. But a lot of it is when we're looking at historic data and developing cost estimating relationships, what we're doing is picking the parameters to allow us to generate these curves within the computer so that the curves are accurate. So calibration, a big part of that in the historic data analysis is all about coming up with the right parameters to shape those curves. So now we've got total effort for a project. We've got the total duration for the project. And we can also now generate some other cost-related outputs. So for example, we can generate we can use templates to generate a template project plan, which is basically an allocation of the effort to the various phases. We can use templates to generate a breakdown by role and by sub-role. So for example, developer, tester, project manager, that's basically an allocation problem at this point in time. We can even do a sub-allocation where developer, we can break it down and say Java development versus COBOL development versus .NET, whatever. We can also generate non-cost outputs. So these would be things that would be predictors of engineering artifacts that will be created during the project and that will be useful from a project management perspective, but that aren't going to be delivered or aren't part of the delivered functionality at the end. So examples would be engineering documentation, lists of documents but with page count predictions, number of test cases. If we're in an agile development environment, it might be things like the number of stories, the number of features, the number of epics. And then finally, we can use a completely separate set of models, but with the similar inputs, and those are going to be able to allow us to do things like forecasting lifecycle support costs. So what's the cost to do different types of maintenance on this code after it's deployed. What's the cost to do operations of it? What's the cost for doing help desk support of it, etc. Now, when we look at estimation, what we find is that if I go back to the ICEAA measures of goodness of an estimate, good estimates are accurate, they're comprehensive, so they cover all the work that needs to be done, they're credible, so you can justify them, you can explain them, and somebody, an objective person, would understand and believe what you're telling them. They're replicable and auditable, so there's no magic involved. Somebody else can come by, follow the steps that you followed, and it's going to end up with the same answer that you ended up with. They're timely, meaning that they can be created in a fashion or in a time frame that's appropriate for where they're needed. So it doesn't do any good to say, well, I can give you an estimate, but only in 3 months, if in 3 months you're already in the middle of your build phase. So it has to be reasonably timely, and they're traceable. And traceability is an aspect of estimation that's often neglected, but it offers an incredibly strong value added to the business. Basically, what this says is we should be able to trace it at the highest level. Is simply tracing it back to the various components that went into it. But what we really want to do is we want to be able to do traceability all the way back to the business requirements that we're trying to implement. Because if we can trace our estimated costs back to individual components of the business requirements, that allows the business users to make educated decisions about what they want to keep in and what they want to take out of the program. I'll give an example. We did a deployment where we added this traceability level to the estimates within Procter & Gamble. And what we found is without making any rule changes, without any organizational policy changes, whatever, that they were able to reduce their information technology costs by 30%. And the way they did that was the business users would now be able to look at, well, here's my list of requirements I gave you. Here's the costs allocated to each one of those requirements. Well, gosh, this one's not worth it. This one's not worth it. Skip this one. We'll change our manual process on that one. And so the business users on their own went through and modified their requirements intelligently based on understanding what the costs were for what they were asking for. And that ultimately resulted in a 30% reduction in the costs. Once again, back with ICEAA, some of the things cost estimating cannot do is be applied with cookbook precision, produce results that are better than the input data. So if you do get garbage in, you get garbage out. But a big part of estimation process improvement is improving the way that input happens. You can't just say, well, we don't have good requirements, therefore we can't do good estimates. It's part of the job of the estimation process to have a mechanism in place to help ensure that good requirements will be generated. Now, we can't say, well, we don't have good requirements, so we can't do anything. What you can say is, if the business doesn't understand what they want, then we can't do a good estimate. If the business knows what they want, but the requirements aren't clear yet, then we can be part of that process of clarifying those requirements. However, if the business doesn't know what they want, then it really is not ready to estimate at all. We can't predict things like political impacts, so we can't do things, for example, of saying, well, what would happen if the project's canceled? You know, what would happen if the project sponsor leaves? Those are types of things that we can't really estimate for. And we can't substitute for sound judgment, for good management, or for control. One of the things that I like to say is that a good, accurate estimate tells what can happen. It does not tell what will happen. You can take the best estimate in the world, and you can get in there and screw the project up, and the estimate is going to be completely wrong. In fact, maybe the project is canceled because it was completely poorly managed. But what we can do is we can set off a project that has a good plan at the beginning. And so at least it has a good shot at at coming in right, which has a significant improvement in the success rate on projects. And then finally, we can't make final decisions. As an estimator, we don't say what should happen, should you do this, should you not do that. All we're really doing is saying, here's what the forecasts tell us going forward. Now let me take just a break for a second and take a look at, see if there's any questions here that we need to address. I've got notes here. I am still seeing only slide 8. Are people? Yeah. Okay. I don't see anything else. The I'm supposed to let people know that the recording, that the webinar is being recorded, which I would now tell you. I've got a question coming in. I wanted to know how to achieve the curves you were talking about. Okay, let me close this back. I'll answer that and then I'll keep talking here. So let me just kind of the process of coming up with the curves is relatively straightforward. So let's start with the simple example. Well, first of all, let me tell you that in general, most of the estimating models use a power function. And a power function is of the form of where the results in terms of effort for a given domain or given type of work is equal to a linear constant. So it's often called alpha, but it's equal to a linear constant multiplied by the size of what we're trying to do and then raised to a power. And so that power, the thing that we raise it to the power is what ends up giving us the economies or diseconomies of scale. So let me give a fairly simple example of, let's say that we were trying to develop a model for doing pages on a website. All we're going to look at is pages. So now let's say that we go back and we look at, and let's say that that was all the work, that maybe we have a special group that they don't do the back-end work, they don't do reports, they don't do the database work. All they do is do page layouts. Okay, so we'll keep it as simple as possible just to illustrate this. So now what I can do is, let's say I've got 5 projects, and let's take the linear case first because that's the easiest. So let's say that on the first project that they did 5 pages and that they spent 50 hours of work to do that. So it's fairly straightforward. I can take 5 pages divided by 50 and I come up with 10 hours per page. No problem there. Now let's say that we have another project. They did 100 pages, and on that project, so it's 100 pages. I'm sorry, that's 5 pages, and it's 50, and so that was 10. So if we did 100 pages, and let's say that that was 1,000 hours of work, so we're still at 10. Everything's linear, so fairly straightforward. But now let's say that we did the project with where it was 100 pages, and instead of 1,000, it was 900. Well, so now we know that we have to have a variable to shape for that. So it's basically, if we have, let's say, a half a dozen or a dozen of these data points like this, in theory you only need 3, but it's better to have more to do better curve fitting. It's basically a question of doing a curve fitting through that. Now there's a kind of 2 different approaches to it. An approach to get you pretty close, and the mathematically correct approach is that it's going to be hard to do without a whiteboard, but I'll explain it briefly. You convert all of your data to log space. So you basically take the log of all the data elements and the result elements, and then when you have a curve like we're describing, a power function curve, in log space it will become a line. So now you can do the slope of the line. Then you convert that back from log space back to normal space, and then that gives you the value for the power function. So that's, in a nutshell, that's basically how you do it. All right, let me move forward and I'll come back for more questions in just a bit. All right, so when we're doing the estimate, what we want to do is, number one, start by determining the estimate purpose. Are we estimating this to do a trade-off? Are we estimating this to help with an acquisition? Are we estimating this to help with a budget? Because understanding the purpose of the estimate will often guide some of the decisions that you're making in terms of how you attack the problem, how you structure the results, etc. Then, very importantly, we want to define the estimate boundaries. So what's the scope that's included in our estimate, and what's the time frame that we're looking at? I mean, are we looking at through delivery of this system? Are we looking at through the first 5 years of operation? Are we looking at through delivery of the system plus the warranty work? So what's the time that's involved? What are we specifically excluding? So perhaps we're excluding hardware costs. Perhaps we're excluding support by the line of business to do user acceptance testing. So what are we excluding? And what are any constraints that we need to be aware of? So is this, for example, is this a very rushed project that has to get out the door very fast because of regulatory requirements? Something like that. We should note that the estimate boundaries may be different from the project boundaries. So the project may have certain responsibilities and requirements, but maybe some of it was estimated. For example, maybe the hardware, we have a bid from the vendor, we know exactly what that amount is, and they said exclude the hardware because we've already got that, we don't want you to worry about that. So it's part of the project budget, but it's not part of what we're trying to estimate. Then, if we need to, we can break the project down into basically an estimate work breakdown structure, which is major pieces of the estimate. So we might want to, for some reasons that we might want to break it down, or some areas, when we're doing this breakdown, when we're looking at it, we might need to structure the breakdown to apply different estimation techniques. So for example, the approach to estimating help desk is different from the approach to estimating data conversion, which is different from the approach to estimating the hardware. And so that's one way that we can break it down. We might need to break it down to support analysis. So for example, if our what-if component is, should we do this onshore versus offshore? Well, we want to make sure that the estimate, the approach that we use, will allow us to break that out. Or we're not sure if we're going to make versus buy for this component. Well, we want to make sure that the cost of that component in terms of make versus buy is clearly and explicitly called out and not buried in some other numbers. Third area is to support acquisition. So for example, let's say that we know that we're going to hire one vendor to do the implementation work on this. We're going to hire a different vendor to do system integration. We're going to hire another vendor to do project oversight, and maybe another vendor to do QA. Well, we want to break our estimate down along those lines. If we're doing an independent government estimate, or if we're doing an estimate as part of feasibility or for cost purposes, for budgeting purposes, we want to break our estimates down that same way so that those are all traceable back to the individual acquisitions. Another reason to do the breakdown is to support earned value management. Earned value management, kind of the easy part of earned value management is tracking effort and costs that have been expended as of a given date. The more difficult part of earned value management is tracking the work that has been completed or accomplished. And so we can actually structure our estimate in a way that we'll be able to measure and verify the work that's completed. So once again, by having the estimate in the form of these high-level objects, which are traceable back to useful functionality, that actually inherently supports an improved earned value management. And then finally, estimation would often align with other control points in the work breakdown structure that is being structured for a major acquisition. In terms of estimation, there's different approaches. One is catalog lookup, where basically what we do is we know that we want to buy this particular model or this particular server. We go to a catalog of some kind, maybe a GSA schedule in the GSA Advantage, and we look up what the price is. Another way to do estimating is learning curve. Isn't used very often in the software world, but it's used quite a bit in manufacturing. And basically this says if you're doing the same activity over and over and over again, that you're going to get better and better at it, and there's definite models and definite equations that can be used, these learning curve equations, to help determine or help quantify how much improvement you're going to get. Where you can use learning curve for software is things where you have repetitive kind of processes, like for example, let's say that you're using a Kanban type technique or it's a queuing technique to manage maybe your defect repairs and your other maintenance work orders that are coming in for small amounts of work. You know, there are 20, 30, 40, 80-hour kind of pieces of work that are coming in and they're being queued up. Well, maybe instead of doing standard estimation, a learning curve approach might work better there. Analogy, you're just basically saying this project is similar to this other project, and then you're making adjustments based on the differences between the two, and then you're going to use that as your number. And then we have parametric. And parametric, there's the high-level parametric, where you're estimating in terms of things that are only nebulously related to the actual functionality that's being delivered. An example would be with satellites. Maybe you're looking at the weight of the satellite tends to be related to the cost of the satellite. Really through a historic, really more of a historic accident. It just happens that they're correlated. This kind of using that to do it, that type of parametric estimation is very high level. And it's kind of risky because if technologies change, if the underlying assumptions change, the parametric curves may not be applicable at all. But then there's a different kind of parametric, which is the parameterized catalog that I talked about earlier, where we have high-level objects that do relate to the delivered business functionality that's going to be there. And what we have is for each one of those high-level object elements, we have some kind of a size equivalency that's assigned to it. A relatively well-known, famous example of a high-level object catalog is function points. So in function points, we have external inputs, external outputs, internal logical files, external interface files, etc. There's 5 different types of elements in the high-level object catalog, and there's an equivalency assigned to each of those, which allows you to calculate out the function points. And then finally, we've talked earlier about bottom-up, where you're basically decomposing the work to be done into the activities, and then you're having people estimate the work required for each one of the activities rather than the actual deliverables, and then you're summing that up. Now, when we look at requirements analysis, there's 3 different levels of requirement definition at work when it comes to information technology projects. The first of these is high-level business goals and objectives. So this is normally the starting point for a project. The business users will define why are we doing this? What's the goals? What are the objectives? How are we planning to do this, etc. Those are normally not adequate for estimation directly. So they certainly are useful. They're certainly important. But we normally can't just take those and immediately convert those into an estimate, at least not very well. Then at the bottom of the scale there, we have technical requirements. So these are things that are unambiguous, they're testable. A developer can write code to them. A tester can verify that they're correct or not. So these are the requirements that we ultimately need to have when we're building software. Normally, the problem with technical requirements are very easy to estimate from. However, the problem with technical requirements is that they're not timely. They're not available until very late in the development cycle. So what we need is something that's more detailed than business goals and objectives, but less detailed than technical requirements. And so this middle ground is what I call high-level business requirements. And so these are things that are high-level aggregations of the technical requirements. And so, for example, a technical requirement, we might, for a given application, we might say, well, we need this particular screen containing these particular fields and these data validation rules on those fields, and this other screen, and here's the screen flows, and so on. High-level business requirements might say we need between 10 and 15 new screens. So we don't know what's on the screens yet. We don't know what the fields are. We don't know what the screen flows are. We don't really even know if it's 10 or 12 or 13 or 15 screens, but we know that we're going to need between 10 and 15 screens of some kind. So that would be an example of a high-level business requirement. So what are some characteristics of good high-level business requirements? They're unifying. They're understandable to both business and to technical stakeholders, and both of them can relate to it. So a screen is a good example. A business user understands what a screen is. A technical person understands what a screen is. Now, they might view it from a different perspective, but they both understand the concept of a screen. Some examples of things that are not good business requirements, not good high-level business requirements. Well, source lines of code isn't very good, because source lines of code is very understandable to the technical user, but it's not very understandable to the business user. Conversely, something like improving retirement planning capabilities. Well, that may be very understandable to the business user, but it's not very understandable to the technical user. So what we're looking for is something that's unifying, that's understandable to both. It should be deliverable focused, not activity focused. So something like write test cases is not a good business requirement. It should be comprehensive. We want to make sure that we're capturing all of the required delivered functionality. But it also needs to be unique. We don't want it to be redundant so that we're double counting work. And finally, it needs to be aligned. It should provide an access point into the estimation process. It doesn't do any good to have a business requirement if it's not useful to us in terms of estimation. There's additional elements of requirement definition that either need to be explicitly gathered, or at least they need to be implicitly gathered so that we can use them in our estimation process. We need to know what must be delivered, and for those things we need to know how many. So yes, we need some reports, but is it 1 report? Is it 10 reports? Is it between 20 and 30 reports? We need some kind of an indication. We need to know what's, for the functionality that's being delivered, how much of it's new, how much of it's an enhancement to something that's already there, how much of it is test only, how much of it is a repair to something, how much of it is something that's new from a business user, but that's going to involve a lot of reuse, and so we would call that additional. We need to have some indication how complicated or how difficult something is that's being delivered. So yes, if we're doing a report, great. Is it a very simple report, or is it a very complicated report? One nice thing, though, is that if we have counts larger than 30, we can use the central limit theorem to set all the values to average. So if somebody tells me I need to write 2 new reports, I want to try to find out, are those easy reports, hard reports, average reports, what are they? If somebody tells me I need to develop 100 new reports, I don't need to figure out how complicated those reports are. I know that from an estimation perspective, I can assume average for those 100. And then as a minimum, high-level requirements need to form a basis for making informed assumptions about these elements. And kind of the overview of the requirements analysis process, we collect together documents about the project, we triage the documents to identify those that are useful from an estimation perspective and sort out those that are not useful. We review the documents in detail that are useful. We create an estimation worksheet of some kind. We normally do a kickoff interview at that point in time, and during the kickoff interview, we want to ask the business users to explain why are they doing this, what do they want to do. We ask questions about it. Then based on that interview, we're going to obtain follow-up documentation and conduct follow-up interviews. And we want to, as we gather the estimate together, we want to document the various components that we're using to do our estimate in some kind of a folder or something like that. And what this document does is it allows us to make sure that the estimate is credible, that it's replicable, auditable, traceable. It also is going to be very useful when we need to update the estimate, because we're going to have the exact documents that we used as the basis of our estimate will be handy for us when we want to update the estimate. And let me, tips and tricks very quickly. Team interview techniques. Basically, if you're going to have multiple estimators doing an interview, the best approach is to have one person at a time be the lead, do all the talking, and everyone else keeps completely quiet. Estimating versus designing. One of the problems if someone who's technical is trying to do an estimate is it's easy to start to drop into the designing mode. So from an estimation perspective, we may need to know that there's going to be about 10 tables. But we don't care what the relationship is between those tables. We don't care what fields are in those tables. We don't even care what kind of data is stored in those tables. And it's difficult for a technical person to not drop into, well, what's going to be into each table. So we want to avoid designing during the estimation process. The sniff test is basically, do the numbers make sense? Does the approach make sense? Are we getting off base here? And I find that the sniff test is very useful, but it's best to only use it at the end. If you try to use it at each of the inputs to the estimate, you can get yourself into trouble. You're better off having faith in the estimation methodology, getting to the end, and then if you say, well, you know what, my methodology is coming up with 1,000 person hours, and this really doesn't feel like more than 100 person hours, I need to go back and rethink this. When you're validating, if you are going to validate with some of the hands-on folks, I find that it's better to validate time at the component level and with the people that are going to do the hands-on for that component. So let's say that there was an area and you're not, the estimating model is coming out and saying, well, this particular model or this particular component is going to take 500 hours, person hours of engineering effort or developer effort. Taking that to a developer and asking the developer to say, does this make sense, is often a good idea for some of the higher risk elements. But trying to have them look at the whole project makes less sense. I've already talked about accuracy versus precision, and I've talked about the wisdom of crowds basically says that if you have a large and a complicated project, if you have 2 or 3 people each do the estimate independently and then compare the results, you will have a much better estimate than if you just have one person do the estimate. Similarly, if there is only one person, if you are the only person to do the estimate, if you can do the estimate 2 or 3 different ways using different approaches or different ways to attack the problem, that will help you to verify and validate that the numbers you're coming up with are in the right ballpark. Let me take a break here and look at questions, see if there's any questions that people are asking. Yeah, I know that there's a noise in the webinar and I can't figure out what I can do to stop it. So I'm sorry I don't have anything there. Okay, I think we're okay. So let's see, we've got just 1 more minute and there was just 1 more slide I wanted to show you guys. So this is the final kind of the overview of what we do. It's like we talked about earlier. We collect documents, triage the documents, review them, start the worksheet, kick off, blah, blah, blah. Then we prepare our estimate. We would normally do some kind of an internal validation process, so this would be among the estimation team or perhaps by going and talking to some of the technical folks. Then we prepare our estimation report. Then we do external validation where we actually show the report to the various people that are impacted, give them a chance to pick it apart. If in fact they raise valid objections, if there's valid things that we missed, we would revise the estimate approach, we would deliver it, and then archive it. So that's the process in a nutshell. So what I'll be doing during the conference in September is actually taking this and then expanding on this and covering a lot more information, a lot more practical how-to information about how to do this. So with that, I'm going to go ahead and wrap things up and say thank you for attending, and I'll hopefully see you in September.